All right, guys. So we've already taken a look at a few examples of functional transforms. There are a few more that I want to go through because they do show up in differential equations absolutely all the time. The next type of transform, functional transform that I want to take a look at is that of a power of t. So things like t squared, t cubed, t to the 10th, that kind of a thing. So we're going to continue our discussion on functional transforms. This is going to be a new example, number 3. Now, before I start the calculation of the new Laplace transform, I do want to bring your attention to a result that we had previously. And it's that the Laplace transform of 1, if you'll recall, was 1 over s. This is actually going to be an important result in this new calculation, and you'll see where we use it. It's going to be very, very apparent, very, very obvious. Right? So the problem statement is the following. Suppose that I'm given f of t to be of the form t to the n, where n is a positive integer. So it is in the domain of the positive integers. That's the fancy way to say it. So a positive integer. Then find the Laplace transform of this, right? So again, we're going to go back to the definition, or we're going to use more like the definition. And in the definition, if we're actually taking the Laplace transform of t to the n, we're computing the integral from 0 to infinity of e to the minus st times t to the n dt, like this, right? Now, this particular case, um, this is not something that's very easily directly integrable, right? There's going to be some tricks here that we're actually going to end up using. And in fact, when it comes to Laplace transforms, in calculating all of the Laplace transforms that you can find in tables, this trick is actually going to end up being extremely, extremely useful. This type of integral, we're actually going to integrate by parts. And remember that the integration by parts is if you actually have an integral of the form v du, where you have top and bottom bounds, then the integral is u times v, evaluated at the top and bottom bound, minus u dv, like this. And the trick is we're actually going to end up picking a v and a du, and we're actually going to do a little bit of calculus and again integrate this by parts. So here, what I'm going to do is I'm actually going to choose u. Actually, let's do it this way. I rewrote this slightly in a different form. It's usually u dv v du. Keep in mind that it would amount to the exact same thing. It's essentially the chain rule backwards, or the product rule backwards, but this is more customary. So here, if I choose u to be t to the n, then the differential du, well, I know it's t n times t to the n minus 1 times dt, like this. And similarly, if I choose my dv to be e to the minus st dt, then the integral of this, my v, is actually going to end up being something quite nice. It's minus 1 over s e to the minus st like this. Right? It's an exponential. It's easy to uh, do these. So here, one of the things that I can say is that the integral from 0 to infinity of e minus s times t to the n dt, well, it's equal to u times v. So it's t to the n times minus 1 over s e to the minus s times t. And I'm going to evaluate at t equals 0 and as t approaches infinity, minus the integral from 0 to infinity of n t to the n minus 1 times e to the minus st dt like this. Let me clean that up a little bit, like that, right? Now, let's really focus in, more than anything else, let's actually focus in on this part. On top of that, one of the things that I'm going to do, and you'll see the reason for this here in a second as well, is this right here, this whole integral. One of the things that I'm going to do is I'm actually going to call this the Laplace transform of t to the n. And on this side, since we have the minus 1 over s here, so I can't forget that term, so I have minus 1 over s. Then I have t to the n in the numerator. And one of the things that I'm going to do, just to make this very, very, very simple, is this exponential, because it has a minus sign, I'm actually going to rewrite it in the denominator, e to the s times t. And I'm going to take the limit as t approaches infinity and as t equals 0. On top of that, for this whole integral here, and this is kind of the clever bit, I want you to notice that the value of n that we have is a constant. So I can actually pull that out of the integral. And what I'm left with is the integral from 0 to infinity of t to the n minus 1. And in fact, I'm actually going to rearrange these terms so that you can see it very, very clearly. E to the minus s times t to the n minus 1 dt like this. Now, if we focus in on this part, we have the Laplace transform of e to the n, and it's minus 1 over s. As t approaches infinity, right? T approaches infinity in both the numerator and the denominator, right? So this right here is approaching infinity, and that is approaching infinity as well. Both of them are approaching infinity. And this goes back to one of the assumptions that we made in terms of the existence of these Laplace transforms. In particular, we wanted to make sure that these Laplace transforms were decaying or of an exponential type or exponential order. What that literally means is that they must decay in such a way that itself actually decays to 0. So in the limit here, for the first part, as t approaches infinity, that very first portion is actually going to end up being 0. So here we have this part, as t approaches infinity, that has to end up being 0. The next thing is, I think I might have missed a term here. Yes. So let me go back very quickly. Luckily, I caught this. Again, it shows that you have to be very, very careful. Over here, this is my du, and my du is right there. My v is right here, but I'm missing a minus 1 over s term. So over here, one of the things, and I'll put this in green so that you'll keep in mind that I did miss it. So in here, we actually had 1 over s minus sign coming from that, which means that here we have this minus sign, that minus sign is going to turn into a positive one. And since we're not integrating with respect to s, I can pull it out of the integral, and we're now left with this. Okay, so I just wanted to make sure that you saw that. The rest of the stuff is okay. And again, it shows you that even professors have to be very careful with respect to this stuff. So we did end up evaluating this integral at t equals infinity, as you can see there. And now we need to evaluate at t equals 0. Now, if I actually evaluate at t equals 0, that means I'm plugging 0 into there and 0 into there. So we have minus 0 to the n, e to the s times 0. And this very happily just turns into 0. So this whole first term completely disappears. While for the second part, we have plus n over s, the integral from 0 to infinity of e minus st t to the n minus 1 dt. Now this is where the clever part is actually going to take place. If you really take a look at what we actually have right here, excluding the n divided by s, notice that that is by definition another Laplace transform. It is, however, the Laplace transform of e to the n minus 1, right? So one of the things that we can do in rewriting this is we can say the Laplace transform of t to the n is equal to, well, we have 0 from the first part, n times s times the Laplace transform of t to the n minus 1, like this. And this is the relationship that I really want to concentrate on. This is actually what's going to end up giving us the result that we're actually looking for. This right here, even though it doesn't look like much of an improvement, notice that it's what we call a recursive relationship. If I wanted to, let's say, calculate the Laplace transform of t cubed, then one of the things that I would need to do is, since n is 3, well, I would have a 3 up here, and then I would need the Laplace transform of t to the 3 minus 1, or t squared, right? So I rewrote it in terms of a more basic Laplace transform, one in which the order of the monomial has been reduced by 1. Now, if I wanted to find the Laplace transform of t squared, well, I could use the definition or this relationship to find it in terms of the Laplace transform of t, right? So t squared, I need to know the Laplace transform of t. Now, to find the Laplace transform of t, I can use the same definition in order to find that, but I would need to find the Laplace transform of t to the 0. And this is where the magic happens. The Laplace transform of t to the 0 is the Laplace transform of 1, and it's something that we have from previously. So this relationship is a fundamental relationship. This is what we call a recursive relationship. And I'll go through some examples here, and then you'll be able to see how this is actually built up. So we know that the Laplace transform of 1, which is the Laplace transform of e to the 0, we found that to be 1 over s. Now, the Laplace transform of t, right? According to this recursive relationship, notice that n is equal to 1. So we would have 1 divided by s times the Laplace transform of 1, which we actually know, right? We can plug that in. So we have 1 over s times 1 over s, and this is actually 1 over s squared. If I wanted to find the Laplace transform of t squared, well, it would be 2 divided by s times the Laplace transform of t, but we just found that is 2 times s times 1 over s squared, or that is 2 s cubed. I'll do 2 more just so you can see what's going on. So if we had the Laplace transform of t cubed, well, according to our recursive relationship, that would be 3 divided by s times the Laplace transform of t squared, right? But this is 3 times s times 2 s cubed, or this is, I'll write it as 1 times 2 times 3 divided by s to the fourth. One last one, and then you'll get a chance to see what the pattern is. So here, if I was looking for the Laplace transform of t to the fourth, this is 4 times s times the Laplace transform of t cubed, or 4 divided by s times 1 times 2 times 3 times s to the fourth, or this is 1 times 2 times 3 times 4 times s to the fifth. And hopefully you can actually see the pattern here. The pattern should be pretty apparent, right? Pattern. If you keep on doing this, the Laplace transform of t to the n, well, you have to multiply all of the numbers, integers from n all the way down to 1. So it's 1 times 2 times 3 times all the way up to 1 minus 1 times n. And what power is it raised to? Well, the s is raised to the n plus 1 power. This top part, right here, this goes by a different name. This is what they call n factorial, and this is s to the n plus 1. So here, the final result is that the Laplace transform of t to the n is equal to n factorial divided by s to the n plus 1, and this was what we were looking for. Now, there are other ways in which you can actually prove this, but this way should actually be sufficient so you can actually see the power of this recursive power.